Maybe we should get started. I thought someone else was going to make an announcement about the travel forms, but obviously not. No one else is showing up to talk about it. But I guess something has to be done with travel claim forms today if you need to put that form in by 11 a.m. All right, our first speaker this morning is Martin Wainwright from Berkeley, and he's going to talk about practical and information-theoretic limitations in high-dimensional statistical inference.
Okay, so I guess is the microphone on? Take that as a yes. So I guess I'd like to begin by thanking the organizers for the opportunity to be here. It's a real pleasure to visit the Institute. So I'll be talking about practical and information-theoretic limits in high-dimensional inference. I guess for this audience, not much of an introduction is needed. We're interested in the setting in which you're looking at systems, let's say, with p dimensions, taking n observations, and looking at high-dimensional regimes in which p is perhaps of the same order or possibly even larger than the number of observations. There's sort of two distinct issues in this talk that I'd like to focus on, and they're really two different kinds of questions that you can ask in this kind of high-dimensional regime. One question is, what are the performance limits of specific methods? So if you give me some specific method, let's assume that it's computationally tractable. You can implement it, let's say, in polynomial time. It's interesting to understand in what regimes it works, and also conversely, in what regimes does it fail. The second kind of question that I want to discuss today has to do with what are really our information-theoretic issues. You'd like to get bounds and limitations that apply to any procedure regardless of complexity. And I think it's interesting to have results of both types, because then you can sort of compare these fundamental limits and put in context results or guarantees that you have about specific practical methods. So like a lot of work that's going on in these days, many other speakers will be talking, I suspect, about related problems, have already spoken and will speak about related issues. I'm going to be looking at a form of complexity regularization where you're assuming that whatever signal you're looking at, I'll always be calling it some beta star in p dimensions, you assume that it's sparse when represented in some suitable basis. And so this is a reasonable assumption in many settings, in sparse approximation, compressive sensing, subset selection, model selection, in database sketching and computer sciences. All these cases, there's a natural kind of sparsity to the models that people look at. So for the remainder of the talk, what I'd like to do is talk about two canonical problems in high-dimensional inference. They're both relatively simple, but in the analysis, I think some interesting things come out. So the first one is the problem of subset recovery in high-dimensional linear regression. And here I'll talk about two kinds of methods. I'll talk about a practical algorithm, an L1 constrained quadratic program, also known as the lasso in statistics, and prove some results about it. And then I'll contrast these results with information-theoretic results that apply to any algorithm, including algorithms that have exponential complexity. And we'll see that there's some interesting consequences. We'll see that the lasso is optimal in some regimes, but actually suboptimal in others. I'll then talk in the second part about a related problem having to do with high-dimensional eigenanalysis, sparse principal components. Okay, so sparse regression. The problem ingredients are pretty straightforward. I'm going to be looking at a vector beta star in r to the p. I'm going to assume that it has some fixed support set that I'll call S. So beta here is always deterministic. And I'm assuming a model of exact sparsity, meaning that it has exactly k elements that are non-zero. So let me just write this here just so we can refer back to it. So P will be, let's say, the signal dimension. I'll use K throughout as what I'll call the sparsity index. So that's just the number of non-zero elements in this unknown vector. And the support here is just the subset of indices for which it's non-zero. And this support set is the object that I'm going to be interested in. And then in the linear regression model, the observation model is you take n observations that are of this standard form. You take some p-dimensional vector x, you take an inner product, and you add some noise. So I've got observations in the linear regression form. So let me write, let's say yi equals xi transpose beta star plus wi. And so the third key parameter here is n, the number of observations. Okay, so of course there's been a lot of work on this model, and there's many different error metrics that you might be interested in. You might be interested in a predictive loss, something like measuring how well your fitted model does in predicting future data. You might be interested in LP losses between some estimate beta hat and the truth. What I'll be focusing on is subset recovery. I don't care so much about the vector beta star itself. I care most about the support set. I care about these indices here for which it's non-zero. And so my loss function will be this. I'll recover it correctly if I correctly get all the non-zeros with the right sign and correctly exclude everything that is actually zero in the true signal. Okay, so what's been studied in the past is many kinds of L1 relaxations, and there's now a whole very rich literature of work on these relaxations that we heard about a bit yesterday. In the case of having noiseless observations, there's a method called basis pursuit due to Chen, Donahoe, and Saunders, which essentially relaxes a hard L0 problem into something that's easier, a linear program. What I'll be focusing on is the case of L1 relaxed quadratic program, also known as the lasso, which is more suitable when you have noise, when you have these additive noise terms. And so what you do is you minimize a sum of data terms plus some penalized L1 norm where rho of n is a regularization parameter that you're free to choose. Okay, so our goal is exact subset recovery with correct sign. As I mentioned, I'll look at two classes of questions. First, I'll analyze the lasso, which I just described, this L1 constrained QP. And in the second part, I'll talk about oracle methods and analyze the information-theoretic bounds. Okay, so the way the analysis that we'll do works is we'll be looking at sequences of models. So what I've written here is I have three parameters throughout. I've written them up there, P, K, and N, the ambient signal dimension, the sparsity index, and the number of observations. And so what I'd like to do is look at a sequence of these models as N, P, and K all scale in some way. We're looking at high-dimensional problems, so they're all going to infinity at some rate. And I'll be analyzing problems with random designs. So that means that these measurement vectors here are going to be chosen from some random ensemble, perhaps Gaussian with some covariance matrix. And what we're interested in is the probability of success. You as the user are free to choose this regularization parameter. This is a random quadratic program. You solve the lasso. You get some estimate beta hat. Beta hat specifies some signed support. And then you assess whether that signed support is correct or not. And what we'd like to do is understand what sort of scalings of this triple, how does this probability to behave? When does it go to 1? When does it go to 0? What can we say about these sequences? So if you actually implement this and you look at different problems, you'll generate curves like this. What I'm showing you here is if you choose your measurements from a standard Gaussian ensemble, this is a fairly standard choice that many people have looked at. If you take your K the number of non-zeros to be some fractional power, something like root p. So root p of your elements are non-zero. And then you run the lasso for various choices of p, 128, 256, 512, and plot number of samples versus the probability of recovering the correct support. So what you see is curves like this. For smaller problems, medium, larger, they're shifting to the right. So the effective number of samples that you need, of course, increases as the size of the model grows. So essentially what we'd like to do is try and understand what's the right scaling. Right? There's this shifting that's happening because the model is growing, so the sample complexity, the number of samples you need, is growing. We'd like to understand what's the right scaling as a function of p and k to make all of these curves line up. And if you find the right scaling, then you can rescale things and instead plot as a function of a control parameter. I'll specify this in a minute. And now, independently of the problem size, the curves are all stacking. So what you're seeing here is that empirically there's a kind of threshold in the performance of this method. Independently of problem size, there's sort of a critical level of observations at which the probability of success transitions from effectively 0 up to 1. And we'd like to understand that. So any questions about the formulation so far? Okay, so here's the first main result is a characterization of that observation, that there is a threshold in the lasso. So the setup is, as I said before, the only additional detail is that you can't have the elements of beta star on the support. Those cannot decrease to 0 too quickly. Obviously, if they go to 0 too quickly, there's no hope of distinguishing them from noise. So they're allowed to go to 0 at some rate. So we have observation noise. We have random design from some appropriate covariance. I'll be more precise about that in a moment. And then the statement is that the right sort of order parameter here is the ratio n divided by k log p minus k. And what that means is that there are constants, constants theta, and these constants depend on the covariance of your design. And on one hand, for some upper constant, if n scales in such a way that it's larger than this quantity, and if you as the user choose rho of n to scale slightly more slowly than this, then in fact the probability of success will go to 1. So that's sort of the upper region. It says that as long as the sample size is so large, then you can choose a regularization parameter such that when you solve the lasso, you will, with probability 1, recover the right support. So just as a comment, of course, there's been lots of past work on related achievability results for things like the lasso for subset selection, particular by Meinhausen and Buhlmann from a few years back. So I'll talk in a minute about exactly how this compares to their result. In the other direction, there's a kind of negative result that I haven't seen in the literature before for noisy problems, which says that if you're below some critical threshold, if the sample size is growing more slowly than this function, then no matter how you choose the regularization parameter, the lasso will always fail with probability 1. Essentially what's happening here is that even though it might be getting almost all of the elements right, there's always some false entries that enter. And that's going to happen the minute that your sample size grows more slowly than this. So that's what's driving these predictions. Sort of part A is telling you the behavior above this point, and part B is telling you that below this point, you're going to 0. So you can look at this sort of different slices. We have a 3-dimensional space, and you can slice it in different ways. What I showed you before was fractional power signal sparsity, meaning that looking at signals where maybe root p entries were non-zero. So that's one sort of slice of this space. But you could also look at a slice in which a constant fraction, let's say 0.1 p, 10% of your entries were non-zero. But if you again plot these things, again, you always see curves when they're rescaled in the right way. They're always stacking. in the way that the control parameter says that they should stack. So let me maybe flesh out a few more details. I haven't really told you much about these constants, and I haven't really told you what this part means. That's a bit vague. What does appropriate mean here? And so the assumptions that we need are, the first one's pretty standard. You need some sort of control on the eigenspectrum of the population covariance of, from which you're choosing the design. The second assumption, this is more problematic. This is, I think, very method specific. It's in some ways an artifact. It's something that's been pointed out in past work, I think initially by Trop and then subsequently by other people. This method needs that you have control on this L infinity norm of the cross covariance between things that are not on, so things in the offset, the complement SC, and things that are relevant in the support. So that's the cross covariance of the population. And then you have an inverse covariance here. And you need that the L infinity norm of this quantity is controlled. So this is known as mutual incoherence or irrepresentability. It has different names. And at some level, it's intrinsic to the method. If it doesn't hold, then you can make the method fail even if you drive the number of samples arbitrarily quickly to infinity. Just to give you precise forms of the threshold parameters, the threshold parameters depend on the eigenvalue bounds. They depend on your incoherence parameter, and they're satisfied for reasonable classes of matrices. Not everything, but certainly things that are interesting design matrices. The case that I showed you, when you have an identity Gaussian ensemble, the sort of standard Gaussian design, that's the easiest case that's been looked at a lot. Then it's very easy to satisfy these criteria. You can satisfy this, of course, with delta equals 1, and you get the eigenspectrum very nicely controlled. And so in that case, actually, the theory gets the threshold exactly. It says the threshold happens at theta equals 1. For more general problems, for instance, toplets, qualitatively you see the exact same picture in simulations. But the theory is weak now. The theory says that above this point it goes to 1, and below this line it goes to 0. So there's clearly some slack in the bounds, but at least qualitatively the same picture is holding. Okay, so let me just sort of mention a few corollaries, some links to past work. So there's been a very nice body of past work on similar phenomena, kind of threshold phenomena, in the case of noiseless observations using the basis pursuit linear program. And as David Donahoe and Jared Tanner and others have described, there's all sorts of very nice geometric connections to polytopes and things like this. The kind of scaling that we have in some ways is qualitatively different. So if, for instance, you imagined that you were working in a regime where n was, let's say, some constant fraction of the model size. So maybe you were working with n equals 0.5 p. You had half as many observations as variables. Then what the scaling that we've predicted, what it says is that the lasso would fail with probability 1 if you tried to recover any pattern, any signal that had linear sparsity. So linear sparsity means that k over p goes to some constant gamma. And the reason that's interesting is because what's known from this earlier work in the noiseless case is that the basis pursuit LP works in this regime. If you give it signals that have constant numbers of non-zeros, so k over p being a constant, then there's some other ratio n over p above which it works. So it is capable of doing linear fraction sparsity with linear observations, but the lasso is incapable of that. So there's some difference, at least for this method, between noiseless and noisy observations. Another kind of scaling, very different qualitatively, that's been looked at by Meinhausen, Buhlmann, by Peng Zhao and Bin Yu as well, is a kind of scaling in which p is actually extremely large. P is actually exponentially large as a function of the number of observations. But then on the flip side, the scaling assumes that the sparsity index k is actually very, very small, that k is sublinear in the number of observations. So you're looking at models in which p is enormous, but k is actually tiny, vanishing extremely fast relative to p. These would be interesting, for instance, in graphical model selection. If you had a graph with p vertices, k would be something like the degree of the nodes in the graph, and it's reasonable and interesting to look at graphs in which the degree is relatively small. So what they showed under this scaling is that then the lasso will succeed with high probability in recovering the sparsity. And you can see that if you look at the threshold we've predicted, if you substitute these kinds of values in, then it's consistent because this order parameter that we defined is actually going to infinity under these three assumptions. Okay, so that's sort of the first part of this first half. What I've done is discuss some results on the lasso, how it behaves for a subset selection loss function. So what I'd like to do now is to do this sort of complementary analysis to consider not just one algorithm, right? I've analyzed a very particular algorithm. It's a reasonable algorithm because it's widely used. They're very fast algorithms to implement it. But you might say, well, okay, you analyze that algorithm. Maybe there's some other algorithm out there that's substantially better. And even more interestingly, perhaps there's some other algorithm out there that has similar computational complexity, it's polynomial time, and is also substantially better. So can we understand whether that's possible or not? And the way to do that is to start analyzing this in a kind of algorithm-independent way, to try and understand what are the limits of this problem just statistically or information theoretically, limits that apply to any algorithm, not just to a particular one. In some ways, this is similar in spirit to minimax analysis. I think the difference is that what I'll be doing really is an average case analysis. Instead of letting nature be adversarial and choose the worst possible signals, what I'm doing is looking at random ensembles of problems and looking at average error probabilities over ensembles. But the spirit is similar. So the way to think about it is to think about the subset selection problem as a kind of what's known as a channel coding problem. So channel coding is just a fancy name for saying you have two people and they would like to communicate information between them. So in our problem, we can think about nature as one person, and nature is trying to communicate to you, the statistician, a subset. So the subset is the message that's trying to be sent over the channel. Now the channel, what's the channel? The channel is simply this observation model that we've specified. Right? We specified that you're taking n IID observations of this form. So that's the channel. You have a sequence y1 through yn, and it's described by some conditional probability distribution. And your goal as a statistician is to try and figure out when can I reliably determine the message, the subset that nature is trying to send me. So what we'd like to do is try and figure out, again, a similar issue. We'd like to look at scalings of the triple NPK. And we'd like to figure out both scalings under which some method is asymptotically reliable in recovering the subset, meaning that the error probability converges to 0. And also, conversely, we'd like to figure out when no method can be asymptotically reliable. When any method has an error probability that is bounded away from 0 as the triple scales off to infinity. So I think this is potentially interesting to do for two reasons. One is that it can unearth regimes in which a method that we already have, the lasso, it can unearth regimes in which that method is essentially optimal. Right? If you compute the bounds that any algorithm has to satisfy, and if the lasso essentially meets those bounds, then we know that that algorithm is basically optimal, and there's less motivation for seeking other algorithms, at least from a statistical efficiency point of view. So that's one motivation. The other motivation is complementary. You might say this kind of analysis might reveal regimes in which the lasso is actually highly suboptimal and suggests that there is some algorithm, perhaps it has very high complexity, but some technique in principle can recover the subset in regimes where the lasso is just incapable of it. And that's also interesting because then that motivates trying to think about other algorithms that might have better guarantees. So the first result here is a set of necessary conditions. So these are conditions that any algorithm that you apply, no matter what it is, no matter what its computational complexity is, under what conditions can you hope that it would succeed? So this result actually applies to any random design with IID entries, 0, mean, variance 1. And what it says is that if you look at the subset selection problem, so it's this setup. I'm thinking about the subset here as being chosen uniformly from all p choose k subsets. So nature is choosing uniformly at random one of the subsets and sending it over this channel. What this result says is that if the number of observations you receive, n, is less than this quantity, this ratio, then no method will ever succeed. And what's in this quantity is sort of two natural things. Log p choose k. Right? P choose k is the number of signals that you're trying to distinguish. That's the number of possible subsets that you're trying to distinguish between. And the logarithm of that is a kind of growth rate, a kind of entropy. And the other thing here is, in some sense, is a second order factor. An information theorist would actually be very interested in this, but for this talk, it's essentially a detail. It's something that tells you how it depends on the signal to noise ratio of your channel. So the key thing here is that essentially log p choose k, up to constants, it behaves like k log p over k. Right? It's bounded above and below by constants k log p over k. So what this is saying is that the information theoretic, at least one direction of it is of that order. So what we've shown so far is that the lasso has kind of critical scaling that's of the order k log p minus k. And what this result, this is 1/2 of it, is saying that the information theoretic decoder has a kind of scaling that's k log p over k. Right? So that might seem subtle, and in some regimes it is actually not a significant difference. So if you think about regimes of sublinear sparsity, think about k being root p. Then log p over root p is like 1/2 log p. That's essentially no different than this quantity. So if your sparsity is vanishing fast enough, if you have sublinear sparsity and it's vanishing quickly enough, then essentially up to constants, the lasso is doing as well as any algorithm could do. Essentially because these two things are equivalent for some scalings of p and k. So that's sort of one conclusion from this. The kind of opposite direction that we can look at is sufficient conditions. We can say, under what conditions is it possible using some algorithm? Maybe it's a very complicated algorithm, but it's an algorithm nonetheless. So under what conditions can we recover? So this result applies only to the standard Gaussian design. So by that I mean I've chosen my measurement vectors as standard Gaussian random vectors. And what it says is that you can recover exactly as long as n is larger than the max of the same thing, k log p over k. And then there's an additional term that depends on, remember, we have to have some control on the minimum value of beta star on the support. That's allowed to go to 0 at some rate, but obviously not too quickly. And so that factor enters here in the denominator. So we can this also tells us some interesting things. One thing it tells us is, let's go back to the case of linear sparsity. Right? Remember, for linear sparsity, we saw that the lasso, if you only give it a linear number of observations, it cannot recover signals that have a linear fraction of non-zeros. And that's true even if you are very nice to it. If you make the minimum stay bounded away from 0, that still applies to the lasso. But if you look at this optimal decoder, if you make this stay bounded away from 0, and you have a kind of linear sparsity scaling, then this term is irrelevant. And this term, p over k, is a constant. And so what it says is that the optimal decoder can, in principle, recover linear fraction sparsity from using only a linear fraction of observations. Right? So this is telling us that in this regime, the lasso is highly suboptimal. Its scaling is completely off compared to an oracle. So it raises an interesting open question. At least to the best of my knowledge, I don't know of any method that people have, a practical method that people have shown that will achieve this kind of scaling. So it's an interesting question. Is there some other method, something maybe a bit more clever than the lasso, some multi-stage procedure, something adaptive? There's a whole wealth of possibilities, but is there some other method, still polynomial time, that is capable of achieving this kind of scaling that the oracle can achieve? So any questions so far? Yep.
Usually in Minimax stuff, when you show something's achievable, you do it by constructing the estimator that achieves it.
Yes.
How did you prove?
Right, so I'll get to the proofs. This is, as you said, a direct constructive. I'll analyze a particular scheme. The other direction is sort of indirect, actually using a Fano inequality, which is often also used in Minimax techniques. So I'll sketch the proofs right now. So overview of proof. High level, I already said this, it's sort of a channel coding problem. You've got a code book which has cardinality p choose k. You're transmitting a subset over the channel. What information theory says, this is a channel, so there's some mutual information that you can define between the output, the observation sequence, and the input, the random subset. And Shannon theory tells you that the capacity of the channel is going to be controlled by that mutual information. The problem, of course, is that it's not in general straightforward just to compute this mutual information. You need to be able to bound or approximate it. So in one direction, we sort of bound the mutual information, and the other direction, the achievability conditions are actually based on direct analysis of a particular kind of optimal decoder. So let me show you that. Yeah, so this is the direct part. This is showing that under certain scalings of NPK, some method, in particular this method, will succeed under the conditions I stated. So it's a straightforward method. It's the natural thing that you would do. It says what you should do is you should search exhaustively over all p choose k subsets of size k. So that already is prohibitively expensive. That's going to be exponential time. What you should do on each subset is you should solve a quadratic program. You should essentially project your data onto the subspace that's indexed by that subset. And then what you should do is output the subset that has the smallest value of the projection. So to analyze this, we're looking at a kind of symmetric ensemble. So we can just assume that some fixed subset is being sent. And what controls the behavior of this method is sort of a notion of interference from nearby subsets. But if you think intuitively, you're sending one subset over the channel, but subsets are sort of packing space in some ways, and some subsets overlap more or less with other subsets. And subsets that overlap a lot, of course, are going to be dangerous to you. If you overlap in all positions except one, that is very likely to cause you problems. So what we do is we look at all subsets other than S, and we index them by their either their overlap or their non-overlap with S. So I'll do it in terms of non-overlap. So T is the number of indices that are in U but not in S. So if T is very small, it means that there's very high overlap. This is very potentially confusing to you. Whereas if T is very large, they're very well separated in some sense. And so the trade-off here comes between how confusing nearby things are and essentially a combinatorial quantity. How many subsets are there that have a certain overlap? Right? So if I have a non-overlap of 1, So everything overlaps except one element. There are actually very few of those. There's only p minus k choose 1 times essentially k. So it's sort of a polynomial factor. As t gets bigger, then you start getting non-polynomial. You get exponential factors. And so what's going to happen is there's going to be a trade-off between the number of possible confusing things and how distinguishable they are. That's the intuition. So a bit more detail. What we do is just a standard union bound. So I'm decomposing it into all possible non-overlaps, the number of non-overlapping sets, and then there's an error probability. This is the key thing that you have to bound. And it's the probability that if you have subsets U and S that have a non-overlap of T, what's the probability that they get confused? And essentially what happens in this decoder is that what it does is it looks at an orthogonal projection matrix onto the orthogonal complement of the subspace. It projects the signal onto that orthogonal complement for the false subset and for the true subset. And it fails if the projected noise is smaller in the false subset than in the true subset. So that's the failure event. And then the sort of bulk of the proof is some large deviations work just to control this probability, to show that this error probability decays exponentially in n and some function of the non-overlap. And then putting the pieces together, you get the bound that I showed. So that's one direction. The necessary conditions in some ways is easier, more direct, fairly standard. We're going to look at a restricted problem where you don't know the subset U, but we're going to assume that on the subset, beta star is just fixed to its minimum value uniformly across the subset. So it's an easier problem, but because we're trying to find necessary conditions, it's okay to relax in this way. Fano's inequality says that the probability of success is upper bounded by a ratio of a mutual information and log of the number of messages that you're sending. And so the only work to be done here is to control the mutual information. And here there's a bit of work to show that we're sort of conditioning, the design is being fixed, conditioned. Mutual information between y and the random subset you can show is upper bounded by n over 2 times a logarithmic quantity of the SNR. And so they're putting the pieces together get you the other direction. Okay, so that's sort of the first part of the talk on linear regression. What I've shown you is looking at two methods. I looked at L1 QPs and showed a threshold of this order. The information-theoretic threshold is somewhat different. It's k log p over k. I discussed these implications that means that for certain kinds of sparsity, the lasso is basically order optimal. It means you might improve the constant, but you're not going to change the scaling in a fundamental way. On the other hand, for linear sparsity, the lasso is actually very far from optimal. Obviously, I've looked at a very special setup. I think there are lots of interesting open directions. The mutual incoherence conditions are very unsatisfying, and there's been some work by Meinhausen and Bin Yu in trying to relax them. I suspect other people here also have relaxations of those kinds of conditions. I think this is an interesting open question, just to reiterate. Is there some algorithm, something better than L1, something a bit more sophisticated that has scaling that's somehow optimal in this linear sparsity regime? To the best of my knowledge, one is not currently known. Okay, so any questions? Yep.
So you say in the beginning, sometimes the lasso can recover this and that problem. Does the smoothing parameter then depend on k?
I guess in the paper I wrote initially, I made it depend on k, but you don't actually have to. You just have to make it decay slightly more slowly than log p over n. And the slightly more slowly depends on how quickly the minimum of beta star I on the support is going to 0.
Because a similar question applies to your optimal algorithm, which you just described.
Yeah, that's a very good question too, right? So my optimal algorithm definitely was exploiting K because it was searching explicitly over all subsets of size P choose K. I think it would be interesting to look at more blind or adaptive algorithms. So yeah.
You can just use the BIC in this case.
Use BIC to sort of estimate
Yes,
K
you
as
will
you
slice
go.
BIC in slices of different Ks, and the analysis will be similar.
Okay, that sounds interesting. Yep.
You used a channel coding argument,
Mm.
but when you first described the problem, I thought you were going to be going towards more of a rate distortion kind of argument, or data summarization, because you want to summarize it into the sparse representation. Does that not work so well?
Yes, that's a good question too. I think it depends on what error metric you're looking at. If you wanted to, let's say, recover beta hat minus beta star in an L2 norm, then that's very much like a rate distortion problem. And then it sounds like you should be setting it up that way and using rate distortion theory. But the way I set it up, I was trying to recover discrete objects as in subsets. So that is somehow very naturally a channel coding problem, hence my use of channel coding techniques.
This question, there are a lot of people here who are experts in this, so maybe they can answer if you can't. But in the statistics literature, there's this whole thing about the lasso is not as good as something called SCAD or something else because it
Jeremy,
doesn't.
we can't hear you at the back.
That the lasso fails compared to, what is it, SCAD or something, in finding the actual, in doing exactly what you're doing. That even in statistics, it's not, well, it's consistent. Is that because in the statistics literature they're letting beta star, the size, go to 0 faster? There's no, why do we say in statistics, where in statistics K is very small compared to P? So it's where, in the regime where you said lasso's fine, there's complaints about the lasso being, quote, inconsistent. Is that because there's no lower bound on the magnitude of B star away from 0? Somebody who works on that?
It's because of multicollinearity, presumably.
There's a multicollinearity.
Yes, because when you start to move away from the Gaussian setup where predictors are fairly orthogonal to each other, if the true model uses fairly collinear covariance, the N1 norm is enormous, and the lasso would actually choose the wrong set of covariance. And it's because you're in a setup where you have collinearity, and that's where L1 methods have an enormous problem.
That mutual incoherence condition that I specified is capturing the notion of collinearity. Okay, so in the last 10 minutes or so, let me just talk maybe a bit more briefly about a related problem, some newer work, but similar in spirit. So it's a problem of high-dimensional eigenanalysis. So looking at principal component analysis in high dimensions. So PCA, of course, is a classical method for dimensionality reduction. But what many people these days are interested in is, again, the high-dimensional analog of it. So you're going to look at eigenvectors taken from sample covariance matrices that are formed from n samples in p dimensions. And here it's known both from random matrix theory and more recent work by Johnstone and collaborators that standard PCA will be inconsistent when you have scalings that don't have p over n going to 0. So that's a very strong condition to require that. So it's natural, again, in this problem to start looking at more structured problems in which some form of consistency or some results might be provable even when you have sort of generic high-dimensional scaling in which p scales in a non-trivial way with n. So there's a nice line of recent work on sparse covariance matrices by Peter Bickel and his collaborators and also Nuruddin. What I'll be talking about is more sparse eigenvector recovery. And here there's also a line of work on this. The problem being here, you want to think about a covariance matrix in which one of the eigenvectors or some subset of the eigenvectors are sparse, and you'd like to try and recover that structure in high dimensions. So what I'll look at here, just to be concrete, I'll look at a spiked covariance ensemble. This is something that was introduced by Johnstone a few years ago. The idea is pretty simple. You think about a sparse vector, again beta. I'll think about the exactly k-sparse setting. And you look at a sequence of what are called spiked covariance matrices. So you take some base matrix, let's say gamma p, and you add to it some multiple alpha times this rank 1 matrix. And if you set things up properly, then you can always ensure that beta will in fact be the maximal eigenvector of this spiked population. So the question's similar. We'd like to think about taking samples from a spiked covariance model like this. The simplest one, by the way, is the spiked identity matrix. That's what's been looked at most in the past. But we'll look at slightly more general ensembles that need not be identity entirely. So with this setup, again, we're taking n observations, and we're asking under what scalings of this triplet is it possible to recover the correct sign support, so the correct k indices along with their sign of this maximal eigenvector. I'm not sure how well this shows. Right, there's some resolution issues here. Anyway, this is supposed to illustrate that you have a population covariance matrix. That population covariance is not a sparse matrix in general. It has a sparse eigenvector. You can't see it here. It looks like the identity, but it's not sparse in general. Its eigenvector is, by construction, highly sparse. The sample covariance matrix is a noisy version. You can see the sample eigenvector here recovers some of the correct indices, but also, because of sampling noise, there's some spurious things that come in. So our problem is to sort of understand what scalings of n, p, and k is the noise in this sample covariance matrix small enough that we can reliably extract these peaks despite the noise. Let me just first analyze a very simple method. This is something that was originally used as a pre-processing step by Johnstone and Liu in some of their work. And it's just motivated by a simple observation that if you look at the diagonal, by construction, for indices that are in the support, the diagonal, the variance is a bit boosted. It's 1 plus alpha, whereas off the diagonal, it's 1 or below 1. So what that says is that in principle, you should be able to, at least in some regimes, if you form the sample covariance and you look at the diagonal of the sample covariance and you form the order statistics and extract the top k, that should work in some regimes. So that's, I'm not so much interested in this. I'm interested in this most just to get a baseline of what sort of a simple and naive thing does, so I can compare that later to a more complex method that I'll discuss. So what you can prove about this algorithm under certain conditions, so I'm looking at spiked covariance matrices of this form. We've got an identity k by k in this block, and some other non-identity matrix here that satisfies certain conditions. We have a maximal eigenvector with k non-zero entries, and its elements are of the order 1 over root k. And what we're trying to do again is recover the sign support correctly. So this is a very simple method, and its sort of threshold behavior is of the order k squared log p minus k. So it's very similar to the lasso. It's just an extra factor of k that you're paying. But in some ways it's appealing because it's so cheap. You just have to form sample covariances and sort the diagonal. And so if you implement this and you again look at similar plots as a function of this order parameter, you see, again, for different problem sizes, the same phenomenon. They all tend to stack up on top of one another for different kinds of logarithmic sparsity, for linear sparsity. Different sparsity, you see qualitatively the same pictures. Okay, so that's a very simple method. What I'd now like to ask is, you can imagine many more complicated methods that are much more computationally expensive. And what it would be nice to see is that by doing more computation, you gain in statistical efficiency. Right? It's interesting to start exploring the trade-off between the computational complexity of methods and statistical efficiency. And you hope that as you ramp up the computational complexity, you get similar gains in statistical efficiency. So the method that we'll analyze here is a bit more subtle. It's due to Aspremont, El-Gawi, Lenkrit, and Jordan from a few years back. And it's essentially what's known as a semi-definite programming relaxation of the problem. So the way it works is you just start with the standard variational representation of an eigenvalue, right? If you have a matrix Q, it's a maximum over the L2 ball of a quadratic form. Now, that problem's kind of unpleasant because it's not convex. You're trying to optimize over the surface of a ball. What's nice is that you can always represent this problem exactly as something known as a semi-definite program, which is convex. So semi-definite program is just a fancy way of saying that you're maximizing a linear function, so trace of z is what you're optimizing, q is the problem variables. So a linear function of a positive semi-definite matrix over the positive semi-definite cone, and you can have other linear or constraints on the side if you want. So this is an exact convex representation of the maximum eigenvalue. And what the relaxation that was proposed is the natural one. If you believe that, in fact, the maximal eigenvector here was sparse, then you would think about imposing a regularization involving, again, a sum of absolute values of the entries of that matrix. So that's the problem that they're solving. You maximize over the positive semi-definite cone. Trace is fixed to 1. This Q here is going to be the sample covariance matrix, and then this is a regularization. So it's very similar, actually, in spirit to the Lassus. So what we prove about this algorithm is the following, that under the same assumptions as before, there's one other technical assumption that we can't get rid of. I don't think it's essential. It's a bit annoying. You need the sparsity to be logarithmic at most. Then we prove that this method, that if you take the rank 1 solution to it, that rank 1 solution from that semi-definite relaxation will specify the correct support of the eigenvector as long as n over k times log p minus k is larger than some critical value. Right? So the upshot here is that you now have two methods. You have a kind of naive method. It has the appeal of being very computationally cheap, so we call this a diagonal cutoff method, and it has a threshold of the order k squared log p minus k. And what this result is saying is that the SDP is much more expensive, but it essentially increases your statistical efficiency by a factor of k. Right? So there's a trade-off here between computation and number of samples that you take. As I said, I don't think this restriction is essential. We can't remove it right now for technical reasons. Right now, we only have a one-sided result. We can only prove that if this ratio is above some value, the method works. But we have very strong reasons, both from these pictures that I'll show you and also just from the nature of the proof. If you look at the pictures, you again see a very sharp threshold. You're choosing this control parameter on this axis, different problem sizes, and you see that they stack up in this way. So we think that it should hold also for linear sparsity. We can't prove that, and we think that it should be a two-sided result, but we haven't proved that either. I'll finish in maybe 2 minutes if that's okay. Yeah. Let me just say a few brief words, very high level about the proof. I won't go into details, but so what we're looking at, remember, is this L1 constrained SDP. This sigma hat, that's the sample covariance, and this is a regularization parameter that the user chooses. At a high level, I think the easiest way to describe the proof is as a primal dual construction. What we do is we analyze the primal SDP, that's this problem, and simultaneously we analyze the dual. And we construct a primal solution and a dual solution, and we argue that under certain scalings of NP and K, we can construct them such that they're primal dual feasible and actually primal dual optimal, and that they have the right properties. So it's sort of a constructive proof. We try and construct this pair, And then we use the scaling of n, p, and k to show that with high probability our construction is successful. So to be concrete, what we're constructing is a primal matrix that's going to be a rank 1 beta hat transpose. That's the eigenvector that we're after. And the dual variables are really Lagrange multipliers associated with that constraint. So you have a whole dual matrix U hat. The conditions that you need that beta hat is always a maximal eigenvector of the sample covariance minus the regularization with the correct dual variable plugged in. We need the sign support condition. That's what we're after. And you need some feasibility conditions. This is the key one. You need that for all elements I, j, and s, U hat of I, j has to be equal to the sine of beta star I, sine of beta star j. That's because we have to get the sign support correct. Otherwise, this is a subgradient. Otherwise, it's sort of free, and it's free to be in the interval -1 + 1. So those are the conditions, and what we do is we break the proof into 3 parts. We look at the difference between the sample covariance and the regularization minus the population. What this amounts to is a kind of signal term. That's the eigenvector you're trying to extract. And this delta is a kind of noise term. That's a noise term that comes from your sampling model. What you as the user have freedom to do is to choose these weights. Those U hats are things between -1 and 1. And you can use those to shift the noise into good directions, to try and cancel or null the noise so that you extract something that's close to this eigenvector. There's sort of 3 steps based on, in the upper left block, we sort of construct the eigenvector so it's correct in this block. And we do that by choosing this matrix. In these 2 blocks, we choose these parts of the dual matrix and ensure that this padded matrix here with zeros is an eigenvector of the full matrix. And in the last part, we sort of have to choose the dual variables in the lower block to try and kill off all the remaining noise. This block is huge. This block is p minus k by p minus k. So that's the last step. So there's some work in those steps, but that's at a high level is the intuition. So just to wrap up, so what I've shown is for high-dimensional PCA, there's an interesting sort of continuum between, at least the start of one, between computational and statistical efficiency. A very cheap method, essentially an order P method, has a threshold of this order, whereas a more expensive method, this is an order P to the 4th method, has higher statistical efficiency by a factor of k. I haven't talked about information theory, but you'd conjecture that the information theoretic limit is again similar to the Lasso. There seems to be some commonality here. And I think there's, of course, many open questions associated with that piece of work. Thanks.
Any questions while Richard sets up?
Just a question about the first part. Contrasted the analysis you gave with min-max at the very beginning, but isn't it true that actually that prior, essentially, corresponds to the min-max solution? You know, picking subsets uniformly at random.
Yeah, I think you could be right. You're saying it's a worst case prior to
Yeah.
the min-max analysis. But the cost is different, right? Right, average case versus worst case.
Yes. Well, yeah, the min-max risk is equal to, you've got equalizers, right? I mean, so the Bayes risk is equal to the maximum risk, the least favorable prior.
So are you saying that if you did the min-max analysis with that as the least favorable prior, you should recover exactly the same result?
One thing that is interesting about Peter's question is if you have, since your predictors have covariance sigma, some are going to be correlated, some others may not be correlated, depends on sigma. So it's sigma where the identity, probably the uniform prior, is going to be close to like the least favorable in some sense. But if you have correlations between columns, then it is possible, as just Peter said, that it the least favorable prior is actually trying to exploit the correlation that you see in sigma to actually hide beta with full knowledge of sigma.
Yeah, that's a good point. The analysis I did only applied to standard Gaussian, so it would be interesting, I think, to redo these things with more general sigmas.